Okay, in this chapter, we will in chapter 3, we will consider how can we solve a nonlinear algebraic equations. You may wonder why we are interested in solving nonlinear equations. The nonlinear equation is problems of solving nonlinear equations is closely related to the optimization problem. Okay, so in many ways. Okay, so this is why. And first we consider the scalar case. Here we consider so in our approach is this. We will consider the scalar case first. Once we understand this, then we move to the multivariable case. Okay. We consider this scalar case first because it's simpler. Then in the scalar case, we consider a nonlinear algebraic function, fx. Okay, fx equals 0, where f is where the function f is a continuous function. F maps R to R, okay, and f is continuous. So I think many of us, or all of us, I believe, are used to get used to some type of function f, right? For example, it's a polynomial. We see this since high school, but in engineering, you'll find that there are many functions more than polynomials. And even in the polynomial probably is the simplest nonlinear function. And we know that for a polynomial, okay, we have analytical formula for computing, for finding the roots of a polynomial. When the degree of the polynomial is not greater than 4. That means we have analytical formulas for computing the roots of a quadratic polynomial, a cubic polynomial, or quartic polynomials. For polynomials of degree greater than 4, there is no analytical formula. I think this is a well-known fact in mathematics, and Abel proved that in the 19th century. I think it's the 19th century, or should be 19 or 8. I think 18 or 19. I'm not sure. Abel is a blind Nordic mathematician. So you see that so even polynomial, if you want to find the root of a polynomial, then analytical methods is limited, but we can always solve that by using numerical method, and this is what we are. This is what we are considering here. Okay. And in this in this section, we will focus mainly on the two methods, which is the bisection and Newton-Raphson. But here today, I think we will cover the bisection method. The idea of the bisection method is very simple. We use the continuity property of the function, because here don't forget that here we assume that the function f is continuous, right? When the function f is continuous, then the values of the function f cannot change immediately, right? And we already know this, right? Then with the bisection, the idea is very simple. Okay, let's look at the figure 3.1 to illustrate the idea of the bisection method. Now, okay, this is the x-axis, right? So when the graph of the function f intersects the x-axis, then that's where the root is, right? At this point, this is the value of the root of fx equals 0, right? Right? Yeah. Okay. So we begin with in the bisection method. Okay. And we start with this proposition. This proposition can be proved using only the continuity property of the function f. So what we have here is we assume that f is a continuous function. And for a given interval, for a given closed interval a and b, if f and fb have different signs, here you see that if fa and fb have different signs, means one is positive and one is, and the other negative, right? Then there exists a root. There exists at least one root of the function f equal to 0 of the equation fx equal to 0 in this interval. Right? The idea is very simple. So in the bisection method, once we know this, then we try to reduce the interval. So we have the interval. When we have the interval, then you see that we now, if fa and fb have different sign, then we know that the root is within a and b. We use 2 points to bracket the solution, the root. What we call it, we use 2 points to bracket the root. Then we make an additional point in the middle. Now we have 3 points. Once we have 3 points, then we only need 2 points to bracket the root of the solution. Okay? The solution. Then how can we do? We check the sign of the middle point. Yes, this is suppose this is f. Okay, we start with interval a naught and b naught, and then we okay. Okay, we a naught and b naught. Suppose x naught is the middle point between a naught and b naught. Okay. Here in the figure, fx naught, it has the same sign as fb naught. Right? So we replace b naught with x naught, and therefore the interval containing the root is reduced by half. Right? Instead, okay, so it's reduced by half. Then the root is now within the interval from a naught to x naught instead of x naught and b naught. Then the interval containing the root is half in each iteration. Once we do this, okay, then we start doing this again until the interval is very, very small. Okay, once it's very small, then it's in numerical computation, we specify the accuracy of the solution. Okay, by the specified accuracy, okay, then we know when we want to terminate. And in computing this, you will say that we need to know only the sign of the function f. Actually, we don't need a value of the function f. We need to know the sign only. This is the minimum requirement that we need. But of course, for most problems, we compute the value of the function f. But I'm just telling you that actually we don't need to know them. We need to know the sign. And it just this is okay. Just in some application, in some applications, okay. It's easier to sometimes it is easier. This is not always the case, but in some cases it's easier to compute. If it is easier to compute the sign of the function rather than the value of the function, then we can, okay, we may use that. Okay, now this is the idea. Then with this, okay, it's already explained the idea, okay, in the slide. You can follow that later. So with the golden section method, Okay, we summarize this in the form of the algorithm. This is what we call the pseudocode. You find this many times in the slide. Okay, with in this, you will see that you can program this in any programming language. Okay. So here in the algorithm we given A naught and B naught. That means to start the bisection method, you have to start with an interval A naught and B naught, for which F A naught is different, has different sign from the F B naught. F A naught and F B naught have different signs. So how can we check? Okay, so in computer, what we do is that to check, how can we check this? So when the function have different, if A and B, okay, A and B have different sign, if and only if the product of A and B are negative, right? If the product of between A and B, if the product AB is positive, then that means A and B have the same sign whatsoever, right? Right? So we use this in the algorithm, right? So we start with A naught and B naught such that A naught and B naught, the product F, okay, F A naught multiplied with F B naught is negative. This is what you have to find first. And once we have this, then we do the iteration. We do the bisection method. Now you may wonder what is I. Here I is what we call, this is the I is called the loop counter or the iteration counter. When we do this kind of method, you see that this is already, you already see this is a kind of iterative method in which we, okay, we solve this in an iterative manner. That means we solve it repeatedly until the approximate or the estimate that we have, okay, converges to the required solution. This is a kind of iterative method. Okay. We do many iterations. I is called iteration, is an iteration counter or loop counter, whatever. And here you see that why we need, what is the role of I? When we do an iterative method, sometimes, okay, you see in sometimes the algorithm does not converge to the solution, and it cannot terminate. When we apply this, you see that how can we terminate from this iteration or from the loops? We terminate this when the interval A and B is small enough. When the interval is small enough, then we decide to terminate. Okay, so the interval AIBI is small enough. It's called termination criterion. So when we implement this as a mathematical expression in programming, then what do we do? BI minus AI, right? Small enough, and that means less than or equal to sign where you specify the sign, right? This is a termination criterion that we will use in the bisection method, or sometimes if you want to do to see this in a in a relative form, then some people maybe use AI minus BI divided by the this is give you some idea, right? Okay, so but for the case of bisection method, usually it's not here we okay we don't have much problem, but with the I think but the bisection method is guaranteed to to converge under certain assumptions. Okay, but for Newton-Raphson, which is another method that we will see on Wednesday, we consider that on Wednesday, and sometimes converges, sometimes it diverges. And in that case, it can be serious. And then, okay, then what we do is that we set the I as the loop counter. Okay, if I exceeds the maximum allowable number, then we terminate the loop. This is what we do. Okay, and usually when we write this as a function, or in Fortran it's called subroutine. In MATLAB or C we call it a function. When you write the function and you apply the function, then when you return from the function, right, you will have a solution. But what happens if you don't have a solution? You need to know, okay, you need to know what happens when the function is called, right? So usually this is what we when we write a function, and if the function can be when the function is not always successful, then you need another variable we call a flag variable to show the status of returning from calling the function. Okay, and then you set up and you set the condition for that, and you look at that. For example, if you may set a flag variable, and you say that if the flag variable after returning from calling a function, if the flag variable is 0, then that means the iteration is successful. Okay, then we have a solution. Or when the flag variable is set to be 1, then the iteration fails, or is likely to fail because of what? And then if the flag variable is equal to 2, is okay, then the iteration may fail because of another reason. Okay, and this is how we know what happens. And if the iteration is successful, then the return solution is the estimate of the solution. Okay, this is how we do this in programming. It's some small tricks, but this is what we use in professional programming. Right? Now, okay, let me just explain this a little bit, and then you can read that at home. Then in this example, we compute the square root 2 by bisection method. What we do is that we form a nonlinear equation. We know that square root 2 is the root of x squared minus 2 equal to 0, right? This is the equation. Then we apply the bisection method. Okay, and in this case, we know that the square root 2 is between 1 and 2. So we start with a naught. We start with a being 1, right, and b being 2, and then we do the bisection method. Okay, and when you do the bisection method, and this is the result. In the first iteration, the midpoint is 1.5. Okay, and we compute the fx naught. Once we have the midpoint, we compute fx naught, right? Then we see the sign of this, and we know that the fx naught is positive, right? Then we set the okay. Then we set B as fx naught. Sorry, as x naught, right? So the A1 is A naught and B1 is x naught, right? And now we do from this, then we do another iteration, then the x and the x1, which is the middle point in the iteration, in the second iteration. And we compute f is 1.25 and we compute fx1, right? And then from here we see that the sign of fx1 is minus. Now it's minus. When it's minus, then we replace a2 with x1, and therefore we have a0 and b2 remain the same as b1. Then and we keep doing this together, and you see that now the midpoint converges to the midpoint. The midpoint converges to is converging to the square root 2, right? After we're doing this, now in this I give you some exercise, okay? And suppose if we start with the A is 1 and B is 2, then how many iterations we need? If how many iterations we require, how many bisections we require, okay? So that the computed solution has an accuracy of at least epsilon. If you want the solution, the solution, let's say with the accuracy 10 to the power of -6, that means the square root 2. We want the value of the square root 2 is accurate up to at least 6 digits. How many bisections you need to perform? Okay, this is something for you to think. Okay, and that's the end of this. Okay, and we'll see you again on Wednesday.